Well, hello, chemistry. Here we're back again for third video of Chapter 8, talking about solubility rules. So get ready for some good stuff here. All right. First thing, solubility. What does it mean? To be soluble basically means that it's going to dissolve. Now, not everything dissolves in water. There are other types of compounds, right? So we could be talking about oil. So oil is a nonpolar compound. We talked about polarity in molecules. And the big rule to remember is like dissolves like. Nonpolar compounds will dissolve other nonpolar compounds. So like oil and gasoline will mix, but oil and water will not, because water is a polar compound. So when it dissolves in water, we specifically say that it is aqueous, meaning that it is already dissolved in water. So to be soluble is a property of it. Aqueous is telling you its state of matter, basically, right now. What is it? So salt is soluble, even in the shaker, right? It's dry. But when I put it in water, that's when it becomes aqueous. So just terminology there, how we're talking about things. So when ionic compounds dissolve in water, they disassociate. And what that means is they get pulled apart. So pull myself, out of the way here. So here we see a salt crystal. It's a nice cubic crystal. And as we think about the water molecule in that bent shape, has a strong dipole, and we know the oxygen is the more negative side of this polar molecule, and so it surrounds the sodium and pulls it off, and then the hydrogen side surrounds the chloride and pulls that apart. And so that's what it's like when it's in water, right? An ionic compound will get pulled apart. Now sugar will dissolve in water, but sugar is not ionic. Sugar is a polar molecule itself, just like a water molecule. So it's just like another water molecule, kinda, and so it fits in with the other ones because they attract to each other, right? So we're going to be talking about ionic compounds and how they disassociate and sometimes don't. Now, sometimes these things hold together so well, the positives and negatives hold together too well, and water can't pull it apart. So when that happens, and so here's the rules that'll tell you when it will dissolve and when it will not. So this is straight out of the book, page 473 in your books. And I'll explain how these rules are set up. These on the upper part, these are the rules that are telling us what will dissolve. So there is kind of a hierarchy here. These upper rules will supersede any lower rule. So I'll explain how that goes here. So let's start with the acetate. So here's acetate, and as we think of whatever's with acetate will get pulled apart in water. So sodium acetate will dissolve in water. You put it in water and the sodium gets pulled away from the acetate. You put calcium in there. Calcium acetate will get pulled apart by the water. Now, there is the exception there, iron 3. For some reason, something with iron 3, it sticks so well with the acetate that the water can't pull it apart. So we would say it's insoluble. It does not dissolve in water. I've talked about this other rule, alkali metals, group 1 metals, lithium, sodium, potassium, rubidium, cesium. All of those will dissolve in water. It doesn't matter what the other part is. Sodium, whatever, it's going to dissolve in water. Sodium oxide, sodium carbonate, sodium whatever, right? Now, the only exception of that is lithium fluoride. Those two lock together and water can't pull them apart. Now, ammonium has no exceptions, right? So ammonium is always soluble, right? So there's no exceptions to that. Bromides and chlorides and iodides, I see a lot of times grouped in with these three, are soluble in water, except with silver, lead 2, and mercury. So, and you see they have the same exceptions, so they do the same kind of thing. And like I said, iodide is normally thrown in with those two also. So, as we think of exceptions here, silver chloride, when those meet up, water can't pull those apart and would be insoluble in water. Nitrates, no exceptions of those. Those are always going to pull apart. It's kind of like the weak link in a chain. You know, start tugging on it, that's where it's going to break, right? Sulfates are also soluble, and except calcium, strontium, barium, lead 2, and mercury. Now you notice calcium, strontium, and barium are all alkaline earth metals, are all right in a row there, and that kind of helps you connect those two, which ones are going to be dissolved or not. So that's the upper rules, right? These are the telling you which ones will dissolve in water. Now these bottom rules, they could pretty much, for most of them, just say, if it hasn't been mentioned up above, it's not going to be soluble. Because that's really what they're talking about down here, like with carbonates. Carbonates, well, are not soluble unless they're with a group 1 metal. Well, yeah, we already said group 1 metals were here will dissolve, doesn't matter, right? Or ammonium, yeah, it's always soluble. It doesn't matter, right? So that's kind of the way I look at these rules. These are the big part. And down here it's kind of like, yeah, you could keep talking about things that aren't soluble, you know, with the exceptions of being with a group 1 or whatever. But basically, you understand which ones will dissolve, and then you know which ones won't also. So chromates is in that same group, hydroxides, right? Oxides, phosphates, sulfides, and so on, right? So as we think of the exceptions up here, this is kind of the big important part of this. Now there are a couple weird ones down here with oxygen, with calcium, strontium, and barium. They have limited solubility. So calcium oxide will make calcium hydroxide, which still has limited, very, very limited solubility. So these are pretty much not going to happen down there. So this is something that I will let you have on a nice piece of paper. You could also add it on to your polyatomic ions, and I will let you use this on the test or the quiz. So as long as you just have this without any examples or anything like that. So when we have two solutions, two things that are aqueous, so we can see this upper beaker is clear, right? We can't see the particles because they're pulled apart. They're like smaller than a water molecule. You can't see a water molecule, so you can't see these things. They're pulled apart. So when you have a solution, it should be clear. It may have a color, like a lot of copper solutions are bluish in color, and irons are orangish in color. But most of them are going to be clear. And we can see in this bottom beaker, it was a clear solution there. But where they meet up, it's turning this brilliant yellow color. And so that means that the combination of these made a combination down here that is not soluble in water. So when that happens, when you have two aqueous solutions combined and you make a solid, that's why we can't see through it. It's not clear anymore. It's blocking the light. That is what we call a precipitate. So that's super useful for us. We're going to do it to use that to identify compounds. So let's look at a couple examples. I'll give you a better idea how these are going to work. So I better get a pen going here too. With this, as we think about, there we go, some examples here. So if I have sodium iodide and lead 2 chloride, well, we look at this. What kind of reaction is that going to be? That's going to be a double displacement or double replacement, right? So we're going to get sodium. I need a thicker pen. Sodium chloride is going to be one of the combinations. This positive can get with that negative. +1, -1, right? So I just better redo this. Sodium chloride. Now, the other possibility is lead getting with the iodide. Lead is a +2, and iodide's a -1, so it's going to take 2 of those. So, as you flip back to your rules, and you look at your rules, and you see, well, is sodium chloride going to be soluble? Well, we can just stop at sodium. It's an alkali metal. It's not lithium fluoride combined. So, boom, we know this is going to be aqueous. We can also look at the chloride and say most chlorides are soluble. It's, ooh, that's not a good, this shouldn't be, that's not going to be aqueous. We needed to have 2 aqueous solutions there. Whoops, I guess I messed up. So this one lead to iodide is also going to be insoluble. It will be a solid, right? Because lead 2 is one of those exceptions of the iodine rule. And so when we see that combined, this is what it would look like. That's the yellow stuff, was the lead 2 iodide. So let's look at another one. I don't think I messed this one up. So with this one, we have silver nitrate. So we have AgNO3. Whoops, I don't want to do that. I already have it over here. Let's erase this one. That was a bad one anyways. So we have, again, a double displacement. Silver can get with the chloride, and potassium can get with the nitrate. No, I'm not going through and balancing stuff up above. I didn't balance that one either. So I want to focus on the rules. So silver chloride. Well, most chlorides are soluble, but silver is an exception. This makes a solid. Potassium nitrate. Hey, potassium is an alkali metal. That is always soluble. Hey, nitrate is also always soluble. So we know for sure that that's going to be aqueous. So when we combine these two and we make a white precipitate out of the combination, we're like, that has to be silver chloride. So let's try another one. We've got nickel chloride and lithium hydroxide. So again, double displacement. Nickel has a +2 charge, so it's going to take 2 hydroxides. And lithium is a +1, chloride's a -1. Again, I'm not balancing. So we look at our rules. Lithium, again, alkali metal. It's not fluoride, so I know I'm okay. Again, I could also look at the chloride side of things, and that's not one of the exceptions of the rule. Now, I come here. I don't see anything rule about nickel up in the top half, and I don't see anything about hydroxide in the top half of the rules. So this is basically getting down to that lower part where it says, well, it hasn't been mentioned up above. This is not going to be soluble. So when we combine these two solutions, both of these over here are aqueous solutions, we get a precipitate out of it, the lithium or the nickel hydroxide, nickel 2 hydroxide. That one is. Okay, let's try another one here. So we've got silver nitrate, and again we'll mix that. Silver is a +1, chromate is a -2. So we see that. And then the other combination, sodium nitrate. Well, hopefully you're starting to see how this is working out. Nitrate has no exceptions. I don't need to look any further. Boom. That's aqueous. I look over here. I see silver is an exception to a lot of rules, but there is no silver rule. And chromate is not in the top half. It's one of those bottom ones that they said is normally not soluble unless it's with an alkali metal. So guess what? That's our precipitate. So here's silver chromate. That's kind of pretty. So let's do one more. This one's tricky because this one, we're making a precipitate, copper 2 hydroxide, but I want to make this precipitate, but then I don't know what I'm starting with. So we think about this, and it's like, okay, well, I need to have copper something, and I need to have something hydroxide. So combining these two through our double displacement will make the copper 2 hydroxide, which is not soluble. So now I need to think of a way to make this aqueous. What could we put with copper to make it aqueous? Well, we could put it with nitrate. Nitrates are always soluble, right? And it would take 2 nitrates to make that work. I could also put it with chloride or bromide, right? Those are soluble. Let's put it with bromide. Bromide's a -1, copper's +2. So copper 2 bromide is aqueous because of the bromide rule, right? Now we gotta get something to get the hydroxide soluble. So alkali metals work, or ammonium there, so we could put potassium hydroxide. That would be aqueous, right? So both of these need to be aqueous, unlike what I did up here. That was wrong, sorry. But these need to be aqueous to start with, otherwise you won't have a reaction to take place anyways. So filling this in, it's like, well, what's our extra stuff that we have here? Oh, we have potassium and we have bromide. That's the extra stuff that we have. And that is aqueous, right? Because potassium's there. That's all we need to say. So this is how you use those rules. We'll use it to predict stuff. We'll use it to test things out and find out what things are made of. So I'm going to eventually give you an unknown, and you're going to run a bunch of stuff, look for precipitates and other things, and that'll let you identify exactly what was in that bottle. So go ahead and get to work, check out that homework, and I'll talk to you later.